with a question that sounds, well, simple at first, maybe even intuitive.
Yeah.
If tiny things like electrons in an atom behave like waves, are they somehow made up of even smaller waves? You know, like ripples on a big ocean wave.
It's a question our classical intuition just naturally asks.
Yeah.
Right? We try to map the big world onto the tiny one.
Definitely.
But as the material you shared points out, like right away, the quantum realm.
Yeah.
It plays by very different rules.
Exactly. And this deep dive is all about exploring those sources you put together, these articles, notes, all this stuff, to understand what these electron waves in an atom really are, what the patterns they form tell us, and then crucially, to get into that other kind of mind-bending idea you highlighted.
The tinier probabilities of other particles.
Yeah, that one, existing in what we normally think of as just empty space.
That's the journey, yeah.
Right.
We're definitely challenging some classical ideas here. But, in doing that, we uncover some really profound truths
About
the fundamental nature of the universe, really, from how matter itself is structured right down to the reality of the vacuum.
So you handed us this stack asking about waves, and it's taking us, like, deep into the quantum world. Let's jump right into that first question then.
Okay.
Because the sources are pretty clear. Electron waves in atomic orbitals are not composite waves, not like an ocean wave made of smaller ripples.
Absolutely. The material makes that distinction very clear, very early on. Quantum mechanics just gives us a fundamentally different picture.
Right, and the why seems key here based on these sources. It's not that something inside the electron is waving, is it?
No, exactly. It's that the electron itself, it possesses wave-like properties.
Wave-particle duality.
That's it, yeah. And the wave we talk about, it isn't a physical ripple. It's a probability wave. You often see it written as psi, the Greek letter S.
Okay, psi. And that's not a location?
No, it doesn't describe like physical structure or path. It describes the probability of finding the electron at a particular point in space.
You look for it.
Exactly, if you were to measure it.
Yeah.
And the Schrödinger equation, which is, the fundamental equation for this,
Right.
it treats this wave function as fundamental. It's not built from smaller classical waves. That's the core idea.
Okay, that immediately feels less intuitive than the ocean wave thing. So if it's the electron's own probability wave, how does interference happen in the atom?
Right.
The sources say it's the electron's wave function interfering with itself. That sounds, well, like a quantum paradox.
It does, doesn't it? And the sources point to a couple of key quantum principles for this. First, there's quantum superposition.
Meaning the electron can sort of be in multiple states or places at once until you measure it?
Kind of, yeah. It explores possibilities.
Yeah.
And second, really critically, there are boundary conditions. The atom itself sets limits.
Boundary conditions?
Yeah.
You mean like the nucleus pulling it in, the fact that it's confined?
Exactly. Think of the atom like a container for this wave. The sources use a really good analogy here. Standing waves.
Like on a guitar string.
Yeah, a string fixed at both ends, or maybe vibrations in an organ pipe. You know how only specific frequencies, specific patterns, can exist as stable standing waves?
The ones that fit.
Precisely. They have to fit the boundary conditions. It's the same for an electron in an atom. Only certain energy states allow its probability wave to form a stable standing wave pattern within those atomic confines.
So the atom is like the instrument, only allowing certain notes, certain wave patterns to exist, and that's what gives us discrete energy levels.
That's exactly where quantization comes from. It arises directly because the wave function has to form a stable standing wave that fits. The sources also suggest maybe a resonating bell is an even better analogy than the string.
Oh, right, the bell. Why is that a better fit, according to the material?
Well, when you strike a bell, it vibrates in very specific ways, right? Its fundamental modes, its overtones. These are stable, standing wave patterns across the bell's surface. And they're the result of the bell's own structure and vibrations interfering with themselves, not smaller ripples inside.
I see. So the orbital shape is like the bell's unique vibration pattern.
Exactly. It's a fundamental way the electron's probability waves can exist stably within that atom structure. It's not built up from smaller bits.
That analogy helps. It feels more fundamental, less composite. Okay, so observing these interference patterns in orbitals, what does that actually prove, according to the sources? What are the big takeaways?
Well, the sources highlight several really crucial things. First and foremost, it's direct experimental proof of the electron's wave nature. Wave-particle duality in action.
Because without waves, no interference.
Exactly. You wouldn't get those patterns, the peaks and troughs or the nodes.
Nodes, those spots where the probability of finding the electron is zero because of perfect destructive interference.
Correct. The very existence of nodes is a signature of wave interference. And this self-interference also explains why electron energy levels are quantized.
Because only certain energies let the wave fit properly.
Only specific energies correspond to waves that form those stable standing patterns within the atom's boundaries.
Yes. And the actual shapes of the orbitals, the s orbitals being spheres, the p orbitals like dumbbells, those are literally the interference pattern.
That's right. The spatial map of the electron's probability is literally shaped by this constructive and destructive interference. Where the wave constructively interferes, the probability density, which is the square of the wave function, is high.
And where it destructively interferes, like at a node, it's 0.
Precisely. Which confirms the electron's location is a probability distribution, not some fixed orbit like a planet going around the sun.
And all this weirdness, this wave behavior, it's exactly what the Schrödinger equation predicts.
Its success in predicting these patterns is, yeah, a huge validation of the theory. And this whole idea of wave interference isn't just stuck inside single atoms.
You mean it stretches out to how atoms bond, molecules?
Exactly right. When atoms come together to form molecules, their atomic orbitals overlap, and their wave functions interfere. This creates new, spread-out wave functions called molecular orbitals. Constructive interference between the original atomic orbitals, particularly in the region between the nuclei, creates bonding orbitals.
Which holds the molecule together.
That's where the electron density gets concentrated, leading to attraction, yeah. And destructive interference in other areas creates anti-bonding orbitals, pushing electron density away from between the nuclei, which is destabilizing.
So quantum interference is basically the glue holding molecules together and defining their shapes.
It's the fundamental basis for chemical bonds, yes, and molecule shapes, too.
Okay, so the big picture here. The electron's fundamental wave nature, interfering with itself in atoms, interfering with other electron waves in molecules. This dictates the structure, the properties of pretty much everything we see.
That's a great summary of this part, based on the sources, yeah.
It explains energy levels, orbital shapes, chemical bonds. It shows quantum mechanics isn't just math, it's real.
It has very tangible consequences for the physical world. Definitely.
Okay, that clears up a lot about electron waves and atoms, but the sources you sent didn't stop there. You also flagged that phrase, tinier probabilities of other particles.
Right.
And this seems to shift focus from the electron inside the atom to, well, the space around it. Yeah. Everywhere.
Exactly. This takes us to the quantum vacuum. Classically, we think of a vacuum as just nothing, empty space, a void.
Yeah.
But quantum mechanics, as the sources really drive home, shows it's anything but empty. It's actually incredibly dynamic.
And these tinier probabilities, that's what the sources mean by virtual particles, vacuum fluctuations.
Precisely. The idea is the vacuum is constantly sort of buzzing, with these particles popping into existence and then disappearing almost instantly.
Wait, how is that possible? Doesn't that violate conservation of energy? Particles can't just appear from nothing, can they?
Well, here's where another really fundamental quantum principle kicks in, according to the sources, the Heisenberg uncertainty principle. Well, specifically, the version relating energy and time. It'll talk. What this allows, essentially, is a temporary borrowing of energy from the vacuum.
Borrowing energy?
Yeah, for a very, very short time. As long as the energy is paid back quickly, within the limits set by the uncertainty principle, it's allowed. And this borrowed energy can briefly manifest as a particle-antiparticle pair.
Like an electron and a positron.
For instance, yeah. They appear, exist for an incredibly fleeting moment, and then annihilate each other, returning the energy to the vacuum.
So they're virtual because they're so short-lived. You can't just, grab one.
That's a key part of it, yes. They're transient, they don't stick around, and this constant appearing and disappearing, that's what we call vacuum fluctuations.
What's the theory that describes all this? Is there a name for it?
The main framework is quantum field theory, QFT. It's the language physicists use to describe fundamental particles and forces.
Okay.
In QFT, particles aren't tiny balls. They're seen as excitations, like ripples or vibrations, in underlying quantum fields that fill all of space and time.
Fields for everything, like an electron field, a photon field.
Exactly. A real electron is a stable, persistent excitation in the electron field. These virtual particles are just very brief, temporary excitations. They're often called off-mass shell because they don't quite follow the normal energy rules for real particles, thanks to that borrowed energy.
Okay, QFT, quantum fields, virtual particles. This sounds incredibly abstract, theoretical. But the sources really stress this isn't just speculation.
Not at all.
There's actual experimental evidence, things we can measure.
This is where it gets really compelling, and the sources list some amazing examples. These virtual particles, even though they're fleeting, they interact with real particles, and those interactions have measurable effects.
Okay, like what? What did the sources highlight?
Well, one absolutely crucial piece of evidence comes from something called renormalization. It's a bit technical, but basically, when physicists use QFT to calculate the properties of real particles, like an electron's charge or mass, they find they have to include the effects of the real particle constantly interacting with this surrounding cloud of virtual particles. The math needed to make sense of it, to get finite, correct answers, inherently confirms these virtual interactions are happening.
So the sums only add up, right, if you include the vacuum buzz?
Essentially, yes. The math demands it. Then there's the Lamb shift. This is a very small but precisely measured difference in the energy levels of electrons in hydrogen atoms.
Something simple theories didn't predict.
Right, and it's perfectly explained by the electron interacting with virtual photons popping in and out of the vacuum around it.
Wow. And didn't you mention something about the electron's magnetism earlier?
Yes, the anomalous magnetic dipole moment. An electron acts like a tiny magnet, but its magnetic strength isn't quite what the simplest quantum theory predicts. There's a tiny discrepancy.
An anomaly.
Exactly. And that anomaly is explained with incredible accuracy by calculating the electron's interactions with virtual particles, virtual photons, virtual electron-positron pairs, the whole zoo. And the source mentioned the precision.
Was it 12 decimal places?
12 decimal places. The agreement between the theoretical calculation, which includes virtual particles, and the experimental measurement is one of the most precise agreements in all of science.
That is just stunning. It's hard to argue with that kind of precision validating these fleeting particles.
It really is powerful evidence. And there's more. The Casimir effect.
Right, the plates.
You take two uncharged metal plates, put them incredibly close together in a vacuum.
And they attract each other.
A tiny attractive force appears. The explanation involves virtual photons. Because they are waves, they have wavelengths. Between the plates, only virtual photons whose wavelengths fit neatly into that tiny gap can exist.
Like the standing waves in the atom again?
Sort of, yeah. Outside the plates, virtual photons of all wavelengths are allowed. This difference creates an imbalance, a pressure difference from the vacuum itself pushing the plates together.
And that's been measured?
Oh yes, observed and measured experimentally. It's real.
The sources even touched on Hawking radiation near black holes.
Right, where virtual pairs near the event horizon get separated. One falls in, one escapes, making the black hole seem to radiate and lose mass. A fascinating consequence, though much harder to observe directly.
And quantum foam, that sounded pretty wild.
Yeah, that's more speculative, linking to attempts to merge gravity and quantum mechanics. The idea is that maybe space-time itself isn't smooth at the tiniest scales, the Planck length. Maybe vacuum fluctuations make it turbulent, foamy, but that's still more theoretical.
Okay, let's just circle back and make sure we're super clear on the distinction because the sources seemed keen on this. The electron's own probability wave, forming orbitals, that's one quantum thing. These virtual particles bubbling away in the vacuum, that's a different quantum thing. They aren't smaller waves making up the electron's wave, right?
Exactly right. That's a critical distinction the sources make. The electron's wave function, describes its quantum nature, how it behaves when confined in an atom, for example. The virtual particles are characteristics of the underlying quantum fields that permeate the vacuum everywhere. They're fluctuations of the vacuum itself. Both are quantum weirdness, but they're distinct phenomena.
So the electron's wave nature lets it interfere with itself.
And the vacuum's quantum nature means it's full of these fleeting virtual particles.
It really does bring us back to that core idea of wave-particle duality for the electron itself. You mentioned the sources use the platypus analogy again. That felt pretty fitting.
It's a great analogy, isn't it? Is a platypus a mammal, a reptile, a bird? It has features of all, but it's none of them exclusively. It's just a platypus.
A unique thing.
Exactly. An electron isn't really a classical wave, and it isn't really a classical particle. It's a fundamental quantum entity.
And the interference patterns, the diffraction experiments, they don't prove it's made of tiny classical waves. They just show a consequence of its quantum nature, which we describe using a wave function in those situations.
Precisely. The wave function is our best mathematical tool for describing the probabilities of its behavior, and that behavior includes acting in wave-like ways, like creating interference.
Wow. Okay. So we started with what seemed like a simple question from your sources. Are electron waves made of smaller waves? And the answer is a clear no, but the reality, well, it's far stranger and honestly more fascinating. We found the electron's own probability wave interferes with itself.
Creating the quantized energy levels, the specific orbital shapes that define atoms, all predicted by Schrödinger's equation, confirmed by experiment.
And then we went beyond the atom, diving into the vacuum itself, and discovered it's not empty at all.
It's this teeming sea of virtual particles constantly popping into and out of existence.
And crucially, this isn't just theory. The sources showed it's backed by incredibly precise experiments. The Lamb shift, the Casimir effect.
That mind-boggling 12 decimal place agreement for the electron's magnetic moment.
Right. These confirm that the vacuum is this dynamic stage interacting with everything. It completely flips our classical idea of empty space.
It really does. What we think of as solid matter, shaped by these electron waves, it all exists within this incredibly active vacuum.
A vacuum bubbling with potential energy and fleeting existence. It just underscores how much more there is to the quantum world than everyday intuition suggests.
Absolutely.
Maybe the most stunning thing from your sources is just that precision. That we can use these frankly bizarre ideas about virtual particles and vacuum fluctuations to predict fundamental properties of matter.
And have those predictions verified to such an astonishing degree.
Yeah, like those 12 decimal places. It forces you to accept that reality at its deepest level is just fundamentally stranger and more dynamic than we can easily picture.
It certainly does. It really makes you wonder, doesn't it? What other layers of reality are operating just beneath the surface, completely unseen in our daily lives?